Hello and welcome to this section of the Circuit Analysis Tutor. Here we're going to cover the so-called resistor networks where you might see series resistors or resistors that are in series and also resistors that are in parallel. And just so you know, at this point in the course we've only really been dealing with resistors other than our sort of general overview that we gave before. So we're talking about series and parallel resistors, and we'll go about how to recognize that and how to use the knowledge that we're going to gain in this section to simplify circuits. But the idea of things being in series and things being in parallel also is going to apply later on in subsequent lessons when we talk about capacitors and inductors and so on. So just keep in the back of your mind here that as you learn about series and parallel architectures that we're going to talk about, when we get down the road to other circuit components, the equations will look a little bit different, but the general idea will still apply. So it's more broad than just resistors, I guess is what I'm trying to say. But for now, since we're talking about resistors and learning about how to simplify resistor networks, we'll talk about series and parallel. Now we've already mentioned this a little bit in terms of throwing the words around, right? I've done that already because my goal is not really to hide things from you and compartmentalize, but I'm trying to guide you through in the easiest way possible. So we've talked about series resistors, for instance, and that's basically when you have components, in this case resistors, that are basically one right after another, kind of like daisy chained is what I like to call it, where you've got one resistor connected directly to another one, connected end to end with another resistor. So if you were going to draw that in terms of a circuit, if you have a, let's say you have some source voltage here, right? And then if you had some series resistors, then you would have one resistor and followed by another one, and we could have, 10 of these things in a row. We could have 95 of them in a row. It doesn't matter, but we have a certain number of these guys here. And so in this guy, we might want to label this resistor 1, resistor 2, resistor 3, and of course if we had resistor 4, 5, 6, 7, and so on, then they would just be all in a row. Now this guy, this is just for illustration purposes, right? So we don't know the value of these resistors, and we don't even know the value of the voltage source, but we know that if we connect a voltage up across these resistors, then some current will begin to flow, and that current's going to be labeled I. So I'm just sort of drawing it so that you can kind of get a sense for what it is. Now whenever you see this guy, we've actually introduced it already once before. I sort of kind of gave you a sort of sneak preview into it. When you have these resistors in series like this, what it means is the current that's flowing through them, it's the same current I all the way through this thing because there's only one path. You see, the only way that current really, in a DC circuit, which is what we're talking about up to this point, the only way that current really ever changes is if it branches. When it hits a junction point and some of the current peels off this way, some of the current goes that way, then the value of those currents in those legs is different than what came out of the battery. But if it's just one loop, then the electrons that are basically moving around, they're going back around to the source, and it doesn't matter what's in the way. Whatever value of current is here is going to be the same value of electron flow that's here, is going to be the same value of the electron flow here. And what would govern how much current in this circuit? Well, let me tell you that right now. If you see resistors like this, then it's the exact same thing as something like this. So let me draw the source again. I'm going to draw one resistor like this. So when you see some guys in series like this, it's exactly the same thing as some equivalent resistance, and of course the same value of I, of current flowing down there. What it basically says is if you go to the store and you buy 3 resistors of 3 different values and you build this circuit here, then you're going to have some current flowing around, right? And you'll be able to measure that. That's great. And then that's exactly the same as far as a big picture point of view as if you were to take the same source and instead combine it with some equivalent resistance. And then with a single resistor, and if you build this circuit, then exactly the same amount of current is going to flow in that circuit. Now what do you think? What do you think the value of this resistance is going to actually be? Well, in this case, I think I've already even hinted in previous sections, in this case, the equivalent resistance is just the value of R1 plus R2 plus R3. And of course, if I had an R4 and an R5 and R6 and so on, however many I had in series, then that would be it. So we've talked about that a little bit. It's not that hard to understand. When you've got these things, if you think about these things as resistances, this guy is resisting the current flow, This guy's resisting the current flow. This guy's also independently resisting the current flow. So when you stick them end to end, they're all resisting with their own contribution, the current flow. So the total resistance is the sum of how much they're individually resisting the current flow. So you can always do this in an electric circuit. Always, always, always. AC, DC, we'll talk about AC circuits with alternating current later on. But right now we've been talking about this constant current flow of DC current we've been talking about up till now. You can always do that. If you see resistors in a line, then if you want to make your life easier, just add them together, redraw the circuit with the equivalent resistance, right? And as far as currents and voltages and things like that, in the big picture, it's going to behave the same. The two circuits are equivalent. All right, now I want to contrast this with the parallel arrangement. So let me write this down, parallel. If I can write parallel properly. The parallel arrangement. All right, so what would that look like? The parallel arrangement we've also talked about briefly. So here's a voltage source. Here's a resistor. All right, now instead of in series, we kind of branch off and create a new leg with a new resistor. And I can do it again, and so on. All right, and this voltage, we're just going to call it V sub S because that's a source voltage. This could be resistor R1, this could be resistor R2, this could be resistor R sub 3. All right, so this is parallel. So really, you need to make sure you understand the difference more than anything. Series is when the current flows through all of the components in series. That's why it's called that. Parallel means that basically the current's going to come out of the source, some of it's going to split down here, the remainder of the current's going to go this way until it hits this node, and then some of it's going to split here. The remainder of the current's going to go down here, and it's going to follow down here. Here I'm going to recombine with this current, forming this guy, and then I'm going to recombine with what came down here, and then I'm going to go back to the source. So this is what we call in parallel, and you can see the difference obviously because basically in parallel the current branches. That's really the main deal. The current branches because you're hitting these legs and you're going down there. So if you wanted to make an equivalent circuit for what we see here, then it's the same as the following circuit. Obviously, we're going to have an equivalent resistor. I'm going to call it Req, and this will be Vs. So it's the same thing. You can re-represent these resistors as a single resistor that I can put in there, and this circuit is going to have an equivalent resistance that's going to be given by the following. Let me write it in another color just so that we can, get it there. So what it is it's 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot, dot, dot. In this case, I only have 3 resistors, so I'm only going to write 3 terms. But if I had a 4th resistor, a 5th resistor, and so on in parallel, then I would just have more terms. Now this, to a lot of students looks a little bit complicated at first. But really, it's not that complicated. If this is, 5 ohms, and this is, 6 ohms, and this is 10 ohms, then all you do is you put 5 ohms, 6 ohms, and 10 ohms in there. 1 over 5 ohms, you get a number. 1 over whatever ohms, you get another number. 1 over, 10 ohms, or whatever it is, you get a third number. These are all numbers. You add those numbers together, right? So what you're going to have is 1 over the equivalent resistance is equal to a number. To find the equivalent resistance, you divide both sides. You do 1 over both sides. So if you look on your calculator, I'll give you a little hint. If you look on your calculator, if most of you guys have graphing calculators, if you're at this point in your education, somewhere on there is usually a button that says 1 over x. And what that does is it basically, if you stick a number in there, the answer you get back is 1 divided by that number. So if you put 2 in there, then you hit that 1 over x button, it'll give you 1/2 back, 0.5. If you put 10 in there and you hit 1 over x, it'll give you 1/10 or 0.1, and so on. Well, this button on your calculator is something that's going to come in handy, really. You can do it all by hand, that's fine. It's just that when you do a parallel reduction like this, you're going to be doing 1 over some number of ohms, 1 over some number of ohms, 1 over some number of ohms. You're going to get numbers, you're going to add them all together. On the right-hand side, you will have a number, right? On the left-hand side, you don't have the equivalent resistance is equal to this. You have 1 over the equivalent resistance is equal to that. So to solve for the equivalent resistance, you have to do 1 over both sides. So on the left-hand side, if you do 1 over what you have here, you'll get the equivalent resistance. On the right-hand side, 1 over what you arrive at on the right-hand side will get your answer. So just wanted to point that out. It's easy to do, you know, by just typing in 1 divided by in your calculator, but a lot of times you have that button on there that makes it super easy. Now, this should be pretty clear. We're going to do some examples to show you how to use this, so don't stress out too much about it, especially this. Some students a lot of times need some help with understanding how to do that, and we'll make sure and do that here in some more problems. But what I want to do now is teach you about something that most of the books also teach you about. Resistors in series, pretty simple, you just add them together. Resistors in parallel, a little more involved because you've got all this division going on, but that's just sort of what you have to do. Now there's a special case. If you only have 2 resistors in parallel, like if you cover this guy up, and if your circuit is just 2 resistors in parallel, then there's a little bit of a shortcut method. I mean, this really isn't that hard, but there's a little bit of a shortcut method that you can get to. So let me show you, number 1, where that comes from, and number 2, what it is. Because you're very, very frequently in circuits, you'll have 2 resistors in parallel. So rather than do this and 1 over and all that, then it's just a little bit easier to get to the final answer. So let me show you really quickly. What I'm talking about is if you have a voltage source like this, okay, and this is resistor R1, and this is resistor R2. So I'm going to keep it generic because I'm driving a formula for you here. So here's R1, here's R2. So we want to find out the parallel combination of this. So we already know what the equation for that is. We just gave it to you. So what it is 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. Now this is the answer, as I said. You can put the values in here, you're going to get a number, and then when you get that number, you do 1 over that final number. That's going to basically flip both sides over, and you're going to get equivalent resistance is equal to whatever value it is. However, let me show you something. 1 over R1 plus 1 over R2. What if I wanted to combine those terms? It's fairly easy to do because I have 2 terms here. What if I wanted to combine them, these guys here? I would have to find a common denominator, right? Because these are 2 fractions. So if I'm going to do that, I can multiply this fraction by R2 over R2. And I can multiply this fraction by R1 divided by R1, right? So I have changed nothing in this fraction. It's just multiplying by R2 over R2, and I've changed nothing in this fraction, but what I do here is I get a common denominator. The common denominator is R1 times R2. All right, so what you get is 1 over the equivalent resistance is equal to, now we can add these together, it's going to be R1 plus R2 over R1 times R2. Make sure you understand that. I'm just adding these together. Common denominator stays the same. So here is almost the answer. But as I said, we want to find out what the equivalent resistance is equal to. So in order to solve for the left and the right-hand side, I need to divide by 1, or say 1 divided by the left, 1 divided by the right, just to be absolutely explicit. Let me show you what I'm doing here. What I'm doing is the same thing to both sides. I'm saying 1 divided by 1R EQ is equal to 1 divided by R1 plus R2 over R1 R2. So when I say 1 over something, all I'm doing is I'm taking the left-hand side, saying 1 divided by that, the right-hand side I'm saying 1 divided by that. And the reason I'm doing that is because on the left, if you have 1 divided by this, it's going to flip over, so you're going to have REQ is equal to, this is going to flip over, you're going to have R1, R2 over R1 plus R2. Now this is valid for 2 resistors in parallel. All right, so there you go. So this is a shortcut, right? If I have 2 resistors in parallel, then all I have to do to find the equivalent resistance is take the resistor 1 times resistor 2 divided by the sum resistor 1 plus resistor 2. And I know you may not say, well, that's not really much of a simplification, but it actually is much easier just to do this, because if you go over here and do it the other way, then you have to do 1 divided by R1, 1 divided by R2, then you have to add them, and then you have to take the inverse, 1 divided by the answer. It's really not that hard, but this is easier because it's also easier to remember. All you have to remember is 2 resistors in parallel, repeat after me, product divided by sum, product divided by sum, product divided by sum, product of the resistors divided by the sum of the resistors. All right, so that's very important. Now let's go ahead and erase this. Let's work a fairly simple problem. just to kind of give you a little bit of experience on how you might actually use these things to simplify a circuit, because a lot of times, not all the time, but a lot of times, you're given a circuit and you can use some of these rules to simplify the circuit into a simpler state. And I think you've learned by now that if you can simplify anything at all about a circuit, even one leg, if you can simplify it, then if you end up having to do Kirchhoff's laws or anything else, it makes everything else so much simpler. Okay, so here's the problem we're going to work, and you'd see something like this where you would be given, in this case we have a current source, right? And we have a resistor network, all of the values are given to us. And we are told that there is some voltage across this current source. We always know that this is the case. All the current sources, they give you a constant current, but they of course always have to have a voltage across it. So what we're asked in this problem is, given this circuit, what is the value of V, the voltage across this current source? So that's what you would be asked. A lot of times on a test, you're not going to be asked, find the resistor simplification of this network, and then you have to do it. I mean, you might be asked that, but it's a little too straightforward. Most of the time, they'll just give you a problem and say, find the value of voltage V. And you can use anything you want. You can use series parallel reductions like we're going to do now. You can just bust into Kirchhoff's law if you wanted to. I mean, we could write a node Kirchhoff current law there. We could write a bunch of loops. We could calculate everything. And then eventually we get enough things found where we can find the voltage there. And we've done problems like that before. However, we look at this and we realize that there's a lot that we can do. For instance, this resistor is in series with this resistor. So 6 ohms and 10 ohms is 16 ohms, right? And once we get this reduction, we're going to have a resistor in parallel with the 64, and we can keep kind of working our way backwards until we really arrive at one single resistor hooked up to this current source. And then it's trivial to solve the problem. So Kirchhoff's laws you could definitely do. There's absolutely no reason why you couldn't do that to solve this problem. However, because this network is so simple, we can just use series parallel reductions. So unfortunately, when you do this, you're going to usually need to redraw the circuit a few times. So let me just kind of do it like this. You can do it any way you want on your paper. What I like to do is kind of draw a nice little light circle or something around what I'm doing, and I'll draw a little arrow to tell myself or my professor the following. The equivalent resistance, right, is equal to, and we talked about this, resistors in series, you just add them up. 6 plus 10 is equal to 16 ohms. That's all you have to write to indicate to somebody that you recognize this is equal to 16 ohms, right? So then, you know, if you want to do this correctly, if you're saving time on a test, you don't have to do all of this, but really the best thing to do is just rewrite it again. So you have the 5 amps here, you have a resistor here, you have a resistor up on top, you have the 64 ohm resistor here, and now you have a new resistor like this. Now let's make sure we understand what we're doing here. So what we have here, we have 30 ohms, here's 7.2 ohms, here's 64 ohms. Now look what happened. We have a resistor here and a resistor here. We're combining them into another resistance. That resistor is still connected between this point and this point. We've just simplified this. So the final resistor we have is in parallel with this guy right here, because what we've simplified is still connected across the terminals of this resistor, so it's in parallel. So now we stop looking at this circuit, we look down here and we say, okay, what can we do next? You can't really add this to anything because they're not in series. There's branching going on here. But these two guys are in parallel. So get your pencil out and draw a nice little circle here and draw yourself a little note to yourself right there to tell you or your professor what's going on. Now these are resistors, 2 of them are in parallel. So the general form we already know. We talked about that, but we said there's a specific special case. If you have 2 of these guys in parallel, it's their product divided by their sum, product over sum. Say that to yourself. If you're just going to use it a lot, product over sum. That's how you simplify this. So you just say the equivalent resistance is equal to the product, let's do it like this to refresh your memory, R1, R2 over R1 plus R2. So in this case, it's simply 64 times 16 over 64 plus 16. All right? And so when we do this, let's switch colors here a little bit. My purple marker is not doing so well. So when we do 64 times 16, then we do the 64 plus 16 on the bottom, we're going to get 12.8. And I trust that you can do this simple calculation. You do the top and the bottom, and then you divide, you get 12.8 ohms, and that's what this is equal to. So again, we redraw the circuit. So we'll say, actually what we're going to do, let's redraw it over here just so we make sure and have room. So what we're going to have, we'll have the current source, we have the 5 amps going up here. Now we have the 30 ohm resistor right here, so we'll write 30 ohms. We have still the 7.2 ohm resistor here, but then what we're left with here after we've done this simplification is 12.8 ohms. Make sure you understand that. Once we combine these guys, they kind of live in one single resistor, which is now coming down like this, right on the tail end of the 7.2 ohm resistor. All right? So now we look at what we have, and we say, oh boy, I see something else I can do. Now I have this resistor in series with this one. So I can definitely do this. So let me just write a note to myself. Equivalent resistance is 7.2 plus 12.8, which is equal to 20 ohms. So this series combination reduces to 20 ohms. All right, so then I come down, and again, I redraw my circuit. So this is, I know it's a lot of redrawing, but it's easier that way. You have the 30 ohm resistor, and now you have your new resistor that we've calculated. This is 30 ohms, and this is 20 ohms, because we just summed these guys together. So 30 ohms and 20 ohms. So now we just have to simplify this guy, and we see that they're in parallel. So draw a little circle telling professor or whoever what you're doing. So the equivalent resistance, because see, this is again the special case, it's only 2 resistors. If it were more than 2 resistors, then you have to use the full-blown version, 1 over R1 plus 1 over R2 plus 1 over R3, and then when you get that, you take the inverse, 1 over the answer. But in this case, since it's just 2 of them, we have a very simple rule, product over sum, R1, R2 over R1 plus R2. All right, and so what we're basically going to have, R1 is 30 times 20 over 30 plus 20. So you multiply this, you add the bottom, and you're going to get 12 ohms. So just to make sure everybody's on the same page, we have a current source, it's 5 amps, and what we figured out basically from all of this simplification is that all of those resistors basically look exactly like a 12 ohm resistor. They look just like a 12 ohm resistor. And we'll just say that that's the equivalent resistance, right? And we know that there's a voltage across this source, and this is what we were trying to find, right? So how do we do that? We have a known current, we have a known resistance, so we just use Ohm's law, right? So V is equal to IR, because the voltage across this source is the same as the voltage across this resistor because they're in parallel. The current, we already know what it is, it's 5 amps. So what we have is 5 amps flowing through this resistor is going to yield a voltage drop. It's going to be exactly the same as what we have across our source. V is equal to IR. The current is equal to 5. The resistor is 12. So what you have is 60 volts. 60 volts is the answer. So this was a little bit of a pain because there was so much redrawing, but think back to the Kirchhoff's laws, right? That was even more of a pain because we had all these equations, all these unknowns, solving a system, blah, 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 getting everything everywhere. We could have gone that direction here, but we noticed that we could add these guys together and get an equivalent resistance. Then we could do the parallel rule and get another equivalent resistance. Then we could do the series rule again, get another equivalent resistance. Then we could do the parallel rule and get a final equivalent resistance. What this means is if you go to the hardware store and build this actual circuit exactly as it sits, then that means that there's 60 volts across this guy. That's what's required in order to push the 5 amps out to do what you're trying to do here. But it's exactly the same as if you just get yourself a single 12 ohm resistor and stick it across there, you're going to get the same 60 volts across the source. So from a source point of view, let's say you live inside of this power supply, you're like a little animal or something and you're looking out into the world, right? From your point of view, as far as what you're delivering from current point of view and from a voltage point of view, what you have to do, the 12 ohm resistor looks exactly the same as this larger network. From your point of view inside the source and what you're delivering out, power and all that stuff, it's exactly the same. So that's what you're going to come into a lot of times in circuits. Sometimes it's going to be a combination of doing these simplifications. And then in some circuits, like if you flip back to our Kirchhoff law circuits, you'll find out quickly that I gave you a lot of problems where you can't do this all the way to the answer. This is a very specifically crafted problem so that I can teach you how to do this stuff. When you go back to our Kirchhoff problems that you've already done, you'll see that you can't do series parallel reductions for all of those problems. So you definitely require Kirchhoff's laws to solve more complicated circuits. However, a lot of times you can do these simplifications to make your life easier. I mean, if you happen to see in your circuit that you have, parallel business going on here, then why do Kirchhoff's laws for all of these legs? Just combine them. And then you'll get, you have less equations, and then once you get some answers, you can go on and figure out what you need to try to find. So that's it for this section. Follow me on to the next section. We'll do some more problems in series parallel reductions, give you a little bit more practice, because it is something that you're going to do quite a bit in circuits. And also, it's extensible to when we get in the later sections. We talk about capacitors and inductors and so on. You'll see that when those are in parallel and series, somewhat similar rules also apply for those components.